Just let us wait for a few more minutes, after which we can start. Okay, so let us start. Hello and welcome everyone to the week 5 live session on the course Experimental Biochemistry, taken by Professor Shagata Dasgupta and Professor Shomode of IIT Kharagpur. I am Srijan Sen, and today I will be discussing on the week 5 lectures in brief, and also discussing with you people few questions which will help you in solving the assignments and also taking up questions in the future. Okay, so I'm presenting my screen. I guess I'm audible to you people. Good. My screen is visible? Okay, cool. Okay. Okay, so mostly today we would be discussing about, so in the previous lectures we have seen about amino acids, we have heard about proteins, we have seen the different structures of proteins, the primary structure, the secondary structure, the tertiary and the quaternary structure. Then we have also studied in the previous lectures about the amino acids and how these amino acids combine to form these peptides, what are these proteins, then what are the interactions present in these proteins. We have heard about it. So today we would be learning about how can we purify these proteins, or why is protein purification important to us. So in today's class we would be focusing on the purification of proteins, and basically three techniques which actually help us in the purification of proteins. One is your gel extraction or the size exclusion chromatography, one is your affinity chromatography, and the other one is your ion exchange chromatography. Okay. So speaking about the protein structure, so as you all know that all the proteins are So as you all know that all the proteins are composed of your amino acids which are linked together into a peptide chain via your peptide bonds. So we have seen that how these peptide bonds are formed in the last class. And we have also seen that there are basically 20 natural amino acids which form the building blocks of the proteins, and each has characteristic side chains which determines the properties of these amino acids. Like some are basic amino acids, for example your arginine, then you have lysine, then there are some aliphatic side chain amino acids like your valine, then your leucine, isoleucine. Also we have acidic amino acidic side chains like your glutamic acids, then your aspartic acid. Okay, so we have seen how these amino acids combine to form the different proteins and how they are linked via your peptide bonds. So proteins are composed of one or more peptide chain in a three-dimensional structure, which also include linkages with your non-protein molecules such as lipids and carbohydrates. And we know that the combination of the number and type of amino acids and the non-protein components of the tertiary structure is important for the function and the property of the protein, as to how the protein will function, as to what it is linked with, how many proteins are attached to each other, or how many motifs or domains actually are involved in the functionality of the protein. Will these domains be only proteins, or these can be lipids and carbohydrates? So those things will actually alter and actually affect the your functionality of the protein. So coming to the introduction of this chromatography. So the goal of biochemistry is to separate and identify your chemical compounds. So you have a mixture and then you are asked to separate a few biological compounds. Then how do you do it? So you perform chromatography. So the main thing is to separate these compounds. So you have a mixture of say 3 bio compounds, and then you're asked to separate this. Then what you do is, that is the goal of biochemistry, is separation. Now, chromatography is one of the most effective techniques for accomplishing this. So, chromatography actually helps us in performing or separating these mixed compound into the different parts. So what do we do in chromatography? So in chromatography, the substances are placed in a system consisting of two physically distinguishable compounds, in which one includes the mobile phase and the other is the stationary phase. So what are these two phases? What are the characteristics of these two phases? I will be coming to it in my later slides and with a later chromatographic technique. And the molecular species separate because they differ. So how these molecular species differ? So some maybe having different density. Okay, some might be having different molecular weights, some might be having different sizes. Also, if we are running gels, then we can tell whether the protein is folded or unfolded. So depending on this, we can actually separate our two compounds. So these compounds need to have different properties on the basis of which we can separate. Okay, so the different types of chromatography which we use in our daily life, or which you people would be encountering, involves your adsorption chromatography. It also has your partition chromatography, then your ion exchange chromatography, then your affinity chromatography. Also, you would be having the molecular sieve chromatography and other paper column chromatographies, then the thin layer and the gas chromatography. So these are some of the chromatographies which we use in our daily life. So what is the aim and why do we want to purify? So the typical reasons for purifying a protein is to identify the function of a protein. Say we know that enzymes are also proteins. So we need to identify as to, or we need to find out how this protein works. For this we need to purify a protein what we need to purify a protein from the other bacterial proteins which the bacteria also expresses. Okay, it also can have contaminants, it can have different other mixtures from which we need to separate, such that we get the pure form of this protein. And this pure protein, what function this pure form has, we need to sort that out. Also, what this purification step helps us in, it also helps us to identify the structure of the protein. For example, it is present, the protein is present in the presence of, you say, contaminants or different reducing agents or oxidizing agents, so the structure will vary depending on its surrounding medium. Okay, but if we see get a pure protein, it is separated from all types of other surrounding materials. So what we get is the native form of the protein. So that will also help us to determine the structure of the protein. To use the enzyme to generate a desired product for a research project. So now we are trying to what you say is finding out the interaction of different proteins, or we are trying to, or we are doing some drug trials, or we would be using this protein in some therapeutics or diagnostics. So so you would be seeing that in many cases you would be seeing this is 70% pure protein, or this is 80% pure protein, or this has 40% purity of the protein. So this, say, it does not mean that if a protein is not pure, it is not functional. It might be that 40% of the purity of the protein is sufficient for the functionality, for performing its function. So that tells us a lot, and the purity of the protein tells us a lot about how this protein would be interacting with other proteins or the other drugs, or maybe finding out your protein interactions, how these proteins would be reacting. And also it would help, the purity of the protein would help in different commercialization of these, say, your enzymes or these proteins or whatever you get, the drugs and all, and we could be using them in either diagnostics and your therapeutic purposes. Now coming to the key steps in purification. While no two purifications are the same and the separation, scientist is faced with a bewildering variety of techniques available to achieve their goals. The majority of the purification aim achieves the same result. So we can use different purification techniques and what we get is the same result. So the different ways we do it. So these are, we release the target protein from the starting material, after which we remove well of the solids to leave the protein in the supernet. And then what we do, we remove the water to concentrate the protein. After the contaminants are removed to achieve the desired purity, then we go for the stabilization of the target protein. So these are just a few steps. You need not keep them in mind. This is just for your information. Now coming to the first chromatographic technique which we would be discussing about, and it is a very important technique, the size exclusion chromatography, or sometimes we call it the gel filtration chromatography or the gel permeation chromatography, GFP or GPC, GFC or GPC, or we sometimes call it the ACC. So what it uses, and it uses porous particles. So here are a few things which we need to keep in mind. The first thing is that it has other names. One is the gel filtration and one is the gel permeation. The other thing is that it uses porous particles to separate molecules of different sizes. So this is important. We have to separate molecules of different sizes and shape. Then we use size exclusion chromatography. So it is generally used to separate biological molecules and to determine your molecular weights and your molecular weight distribution of polymers. Okay, also it is usually applied to large molecules or your macromolecular complexes such as your proteins, and sometimes your you can tell your industrial polymers. Okay, so when an aqueous solution is used to transport the sample through the column, the technique is known as your gel filtration chromatography. When an organic phase is used in the mobile phase, now when the mobile phase is the phase, so if I tell you in brief what is the stationary phase and what is the mobile phase. So the mobile phase is that particular phase through which your protein would be traveling, or that phase is your traveling phase, whereas the stationary phase is the one through which your protein is traveling. For now you have porous particles. As I was speaking of this porous particles. So what are these porous particles made of? It can be made of your silica, okay, or some other different compounds which actually is involved in the packing of the column. So this chromatography has a large column. So these materials are actually, these porous materials are formed when the packing is done. So this packing is done with different compounds. Sometimes you have your Cepharex or your Dextran. So these are some packing materials. So this is comprises of a stationary phase which does not move, whereas the mobile phase is through which your protein is passing. So that will actually will be your mobile phase. So now when we use an organic solvent in a mobile phase, the technique is known as a gel permeation chromatography. So if an aqueous solution is used, it is gel filtration, and when an organic solvent is used, it is gel permeation. And the separation of molecules is called as fractionation, and sometimes the size of pores in the beads determines your exclusion limit, what goes through the beads and what goes around the beads into the discard. Okay, so what is this exclusion limit? So for example, you are given a limit of 5000 kDa, or sorry, 5 kDa, 5000 daltons. Now what happens? So if you are given a limit, so if a protein having a molecular weight above 5000 daltons, those proteins will pass through the beads and cannot enter the beads. Okay, so they will pass through the bead and they will go into the void volume. So the void volume is one where you are not actually collecting your protein. It goes on with the, when you're washing your column. So washing the column is important. So when you're washing the column, your protein just washes off and it goes into the void volume. Now only those proteins will be inside the bead whose molecular weights are less than equal to 5000 daltons. So that limit actually determines the, and these beads have different sizes. So the size actually also depends, actually tells us the story about your molecular weight, as to how much molecular weight of the protein it can take and discard or let it flow through. Okay, so that is important. So the costly instruments have can purify proteins up to higher molecular weights, like you can say 100 kilodaltons or 200 kilodaltons, whereas some less costly instruments can purify up to only, you say, 20 kilodaltons or say 50 kilodaltons. That's all. Okay, now coming to the principle of this size exclusion chromatography. So a mixture of molecules is dissolved in liquid, which is your mobile phase, is applied to a chromatographic column which contains a solid support from the microscopic spheres or the beads, as I was telling, which means makes your stationary phase. So the mixture of molecules like your proteins and your buffers all would comprise the mobile phase, and the packing of the column will determine your stationary phase. That is a solid support that actually comprise is building the component of your column. Now the mass of the beads within the column is often referred to as the column bed, and the beads acts as traps or sieves and function to filter small molecules which become temporarily trapped within the pores. So the different proteins, not only small molecules but different proteins gets of different molecular weights gets trapped within these beads or these pores, and these are primarily trapped in this. Now what happens, the larger molecules pass around, so the exclusion limit is known to you, because when the instrument comes to you, you are aware of that exclusion limit. Now this exclusion limit, based on that exclusion limit, the higher molecular weight proteins gets excluded from the beads. Now the larger sample molecules cannot or can only partially penetrate the pores, whereas the smaller molecules can access most or all the pores. Okay, so mostly it is cannot, but sometimes it may happen if it is better affinity or other maybe functionality, maybe it's a linear one or not a or highly folded one, so this can happen only partially, but mostly it cannot penetrate the pores, whereas the smaller molecules can access most or all the pores. Now therefore what happens that the larger molecules eludes faster because they do not enter all the pores. Now it is not that the stationary phase is made up of only one size of pores. There are different sizes of pores that are actually inside your column. So there are, say for example, if I'm saying there are bigger pores and sometimes there are maybe smaller pores. Okay, so depending on that, so here your large molecules can enter and here your small molecules will be entering. So depending on this the proteins enter this, but you, as you know, that the easier way it is to enter, the easier it will also be to escape. So the larger molecules can easily enter these larger pores and can also escape fast. So the escaping property of these larger molecules is faster. That's why they elute faster. So what is elution? So elution is when you are so first the protein is trapped inside the pores and then you are passing a buffer which actually releases the affinity from the column bed of these proteins. Now when the affinity for the column bed, when the proteins are not in any way showing any affinity for the column bed, then your protein starts coming down through the column and then what you get is your actual protein. So this process is termed as your elution, and then the smaller molecules elute later. So the larger molecules elute faster, the smaller molecules elute later, while the molecules that can access all the pores elutes last from the column. So if there are some molecules which can enter all the pores, so they will be taking a longer path. So maybe you have been asked to, because they have to travel all the larger molecules. See, like this is the white portion. It can just enter and done. But what happens when the smaller molecules are entering? It is also passing from here, here, then here. It is going there. So the path is longer for this smaller molecule, and also it would be longer for the smallest molecule because it can enter over here, but larger molecules won't be entering and it will just flow through, so they will take less time, whereas the smaller molecules will be taking the most time and will be eluting the last. So particles of different sizes will elute through a stationary phase at different rates, and in this way you can separate the proteins depending on their sizes. See, if you see that this is a porous polymer beads which this column is made up of. So this is the column and the protein mixture is added to the column containing your cross-linked polymer. So this is a polymer packing and then you add your protein. Now the proteins separate based on their size. The larger molecules pass through freely. See, the larger molecules don't enter these beads. They can just flow through. They will be entering only into their sized beads. Okay, so and they can flow through faster, but the smaller molecules, you see, they are um, coming and packing to all the beads and then their path is longer, so they take more time. And you see, this is also the same. So you can see here that the larger molecules cannot enter the beads over here. The red ones are the largest and they cannot enter the beads, and therefore they just don't enter and just escapes these entering process and they just flow from outside and travel faster. Okay, but whereas your medium sized or your medium size can enter a few, but if they do not enter, means if they do not get their bead size, then they cannot enter, and then this is slightly less. But the very small molecules can enter all the beads and therefore they take a longer time. So this is just a schematic figure for your better understanding, like the larger molecules, why the larger molecules travel faster and why the smallest molecules travel slower. So there is sometimes a mistake that when you see the curve, you get a curve. Let me see. Yes. So when you see this kind of curve, so 1, then you 2, then 3, sometimes it's like 1 means the smallest has come out. No. So the first thing which comes out is your larger one, and then is your medium, and then comes your smaller one. So the last one is the smallest molecular weight protein. Okay. So this is actually a calculation where you can calculate your total column volume VT. Sometimes you might be given questions in your assignments regarding this VT calculation. So what is VT? It is your summation of your VG, VI and VO. So what are these three terms? So Vg is the volume occupied by the packing. So how much volume is occupied by because of your stationary phase or the packing. Now Vi is the volume of the solvent in the pore. So how much volume within the pores is your solvent actually acquiring. So that is your volume of the solvent in the pores, and V0 is the free solvent volume, which is almost similar to your injection volume. So these three terminologies actually combine to give your VT value. So this is the same thing which is written over here. So in with different terminologies probably. So V0 is your void volume. So the volume of the solution outside the beads or the elution from very large molecules. VE is the volume from the time of the protein is placed until it appears in the effluent. Now VI is the volume of the solution inside the beads. You do not need to know the calculation. Now VC is the total geometric volume of the column. So better is to remember only this equation. This is a simple equation which will help you. Okay, so VT, another time I am repeating, VT is your summation of number one, the volume occupied because of the packing thing. Number two is the volume which, because of the solvent, the volume which is occupied by the solvent within the pores, and the third thing is the free solvent volume, that is which is similar to your injection volume or the volume if we assume that all the molecules or all the protein molecule will pass through without being um, taken by any of the beams. Okay. So what are the different components of your size exclusion chromatography? One is your stationary phase, one is your mobile phase, one which is very important is the column, the pump, which will actually determine the flow rate and the different things, because these rates, if you go into higher advanced courses of these, you can understand why the flow rate, if the flow rate is slow, what happens, if the flow rate is fast, what happens. So different factors actually affect. So the pump is important, and the last thing and the important thing is detector, where you will be detecting when your protein is getting eluted. So we see protein so when the protein gets eluted, you will see a peak, a very sharp peak. So you are supposed to get a sharp peak, means you're actually loading of the protein, then your protein structure. We can comment on the peaks which we get in the detector. We will be seeing this protein, when the protein gets eluted, we will be seeing an absorption at 280 nanometers. Now speaking of this stationary phase, it is semi-permeable. It has porous beads with well-defined range of pore sizes. So these beads are your cross-linked polymers. So if you ask me what type of questions you can expect, so it can be given in the question, which of these are the characteristics of the stationary phase? Tick them. And it can be an MSQ question where maybe you're given 4 points and out of which 3 may be right. So these may be cross-linked polymers or something is given to you. So that is why these knowing about the stationary phase is important. Then the degree of cross-linking is controlled carefully to yield different pore sizes. Now smaller pore sizes are used for rapid desalting of the proteins or for your protein purification. Intermediate pore sizes are relatively used to separate small proteins. And if we use very large pore sizes for the biological complexes, because it's a complex and it has a large structure. So for very large, when the pore sizes are very large, we use this for purification of biological complexes. Now the stationary phase, which is used for gel filtration chromatography, includes your dextran, which can be this polymer is, or maybe your dextran, then can be your polyacrylamide or your dextran acrylamide, which is also termed as your cefacryl TM. Okay, now each is available with a different range of pore sizes in the beads, permitting separation of macromolecules of different sizes. So the stationary phase can be comprised of different pore sizes, which will also help you in separating different sizes of the proteins or macromolecules. Right. Now, what are the characteristics of a good stationary phase? This is also important to know, because it is good to have a stationary phase, but what are the characteristics of a good stationary phase, that is also important. So it should be chemically inert, that is, it should not be reacting with your proteins or your macromolecules or the polymers or the complexes. It should be inexpensive, that is also very important. It should not react with a component which we are trying to separate. It should not react with the eluent. It should be colorless, uniform in size and shape, and should be mechanically stable. Like when we are starting to elute, it might happen that even your stationary phase is trying to strug off, okay, or is leaking your protein. So that should not be happening. It should be mechanically stable. It should not be reacting with your eluent or your proteins or the macromolecules, and it should be chemically inert. Along with it, it should be inexpensive. Okay, so this is okay. So now speaking of the mobile phase. Now, the liquid used to dissolve the biomolecules to make the mobile phase is called your buffer. The mixture of biomolecules dissolved in the buffer is called the sample. So the sample has to be in something. It cannot be like it's in can be in anything, milky water or autoclaved water. It has to be dissolved in your buffer. So that is your sample. Now the choice of mobile phase to be used in separation will depend on the type of separation to be achieved and the component to be separated. Now this is an important point, because the choice of mobile phase which you use, the pH of such a buffer which you are using, whether you would be using a phosphate buffer or a tris buffer, or whether your buffer should have, or how much salt should your buffer have, and what should be the pH, these things are very important, and it will vary from your protein to protein, or your macromolecule to macromolecule, or your complex to complex, because this will actually affect your separation process and also your purification. So this is important, because it will the type of separation you want to achieve and what you want to separate, that is, for knowing this thing or for understanding this thing, you also have to know the components of the mobile phase which you are using. So mostly the common eluent seen for polymers that dissolve at room temperature is your tetrahydrofuran, then we used chloroform, then dimethyl formaldehyde. So these are some of the names you can remember, not important like that much. And if you have synthetic elastomers, then the solvent which can be used is toluene. If your material is made up of polystyrene or PVC, then styrene, butadiene, then rubber, epoxy resins, then you can use the solvent to be tetrahydrofuran. If your material, that is the material is the stationary phase, and your solvent is the mobile phase. Okay, so if your stationary phase is your polyolefins, then your mobile phase can be trichlorobenzene. If your stationary phase is polyurethane, then your mobile phase could be dimethyl formamide. Now if your separation, the thing you want to separate is proteins or polysaccharides, then you have to use waters and buffers. So this is the material which you are using for separation, okay, and this is the solvent which you would be using for separating these uh, particular materials or these particular components or compounds. Now this you can tell as the entire structure or the entire thing of ACC, where you have, so this is the column, this is your mobile phase with which you would be eluting. Then here what you do, you inject your sample over here, and then it flows through the column, and also with this injection valve you have the mobile phase which will actually push your protein forward and help the macromolecule or your compound to flow through this loop, after which it is being detected in the UV, from because of which you would be getting peaks in the data station. And then after this you would be seeing that you are getting somewhere the you're collecting. So you also have the collection tube where you would be collecting your protein when your protein starts eluting. So you would be getting a peak, say like this, and then you start your elution. Okay, so this is the total structure and the different components which you have. You have the mobile phase, then your injection valve. Also we have the pump, which also which what you call is handles the flow rate. Then you have the detector, the interface, and the data station where you collect the data and save the data. Also with this you have a collection tube in which you would be collecting the samples or the separated compounds. Now why these pumps are important? So a highly constant flow rate has to be, so the flow rate has to be constant, and it should be maintained during your entire process. This is very important for this type of chromatography. A change of the flow rate of only 0.1% can cause an error in molar mass up to 10%. So just a fraction of an error, a percentage fraction of an error can actually cause an error up to 10%. Okay, so the most pumps can only reproduce the flow rate of 2 to 3%, and inline filters in the solvent reservoirs may prevent particles from coming into the pump heads, which might damage the check valves or the pump seals. And what we use is the syringe pumps or the reciprocating pumps. Now coming to the detectors, so we have concentration sensitive detectors, among which we have the bulk property detectors, then we have the solute property detectors, in which you have the ultraviolet absorption detector. In the bulk property detectors we have the refractive index detector, and in the evaporative detectors we have the evaporative light scattering detector. Now the molar mass sensitive detectors, we also have these molar mass sensitive detectors, which includes your light scattering detectors. Then we have the LOLs, that is your low angle light scattering detectors, and MALS, that is your multi-angle light scattering detectors. So these are the few categories of the detectors which we have and which we use. I'm not sure whether you would be getting questions from here, but these are just for your information. So you can keep in mind as to what are the types of detectors you can have, and what you would be using them for. Now coming to the applications, so of this size exclusion chromatography, so this helps in your protein fractionation, it helps in your purification, then your molecular weight determination, which we basically use this size exclusion chromatography for, mostly for purification, molecular weight determination. Then if you have to separate sugars, proteins, peptides, and other polymers based on this size, we can use this. This is basically very helpful. Now this technique can also determine the quaternary structure of the purified proteins. So comments on the structure of the proteins can also be made. So size exclusion chromatography is widely used technique for your purification and analysis of synthetic biological polymers such as your polysaccharides, then your proteins, nucleic acids. Now various species of your RNA and viruses have been purified using your agarose gels. These size exclusion chromatography can also be used for your desalting, then buffer exchange. Okay, and also it can be used for your copolymerization study. So these are the few applications which of your size exclusion chromatography. So mostly we use them for purification. So it depends on the different things you want to separate. So mostly we want to separate a mixture of proteins or the protein of our interest from the other not necessary proteins. and the purification process, and also it will help you to understand about the molecular weight of the protein and the structure of the protein as well. Coming to the next type of chromatography, it is your affinity chromatography. So this technique offers high selectivity, hence high resolution and usually high capacity for the proteins of interest. And the purification that would otherwise be time consuming, then difficult or even impossible using other techniques can be often be easily achieved with your affinity chromatography. And this technique is used to separate your active biomolecules from your denatured or functionally different forms to isolate pure substances present at low concentration in larger volumes of crude sample, and it will also help you to remove specific contaminants. So these affinity chromatography, why this affinity chromatography is important? Because of the few reasons. So one is that it offers you high selectivity, it offers you high resolution and high capacity. So these three are very important. The other thing is that if the purification process is time consuming, okay, then we can use it because it actually reduces the time thing. Then it would be also, if for, so this chromatography also helps when your proteins have affinity for a particular thing, so that thing can be used to make up your column, and then it will help your protein to get attached to that your say column, and then you can actually purify it. So if it is not possible using any other technique, we can use this. And also it is used to separate active biomolecules from your denatured or your functionally different proteins. Okay, and it will also help you to isolate pure substances which are present at low concentration in larger volumes of crude sample, and it also helps to remove specific contaminants, because those contaminants will not be having any kind of affinity, whereas your protein would be having. So this is the principle of your affinity chromatography, you can say, where first you have to inject the mixture, after which your protein or the macromolecule undergoes your adsorption, and then it will be attached to that bead, after which you have to wash out the impurities, because also there would be some impurities present here and then which you need to wash with a different kind of buffer. And then comes your elution process, where you would be using an elution buffer. What happens in this elution process? So these elution process might be having here some ions. So these ions would come, maybe ions or other compounds or components which would be binding to this bead and would be releasing out these, okay, during an elution. So it will release out this and then this, and finally you would be getting your protein of interest. So this is your matrix, then you have a spacer, then you ligand to which your object material is going to bind, and after this happens, then something else comes and binds to this ligand and your object material gets eluted. So in this way you can actually, so this is the total concept. First you have to inject your mixture, then the adsorption process undergoes, and then you wash out the impurities because those won't be binding, and after you use a buffer which is your elution buffer, then you can elute your object materials or your protein of interest or any macromolecule which you are trying to separate and purify. So this is the thing of your affinity chromatography. You can just look at the structure of it, where this is your gel which is through which your protein of interest would be passing, and then you have a small plug of glass wool, and after this, when you pass your elution buffer, then from here you can collect your protein of interest. Now, your affinity chromatography separates proteins on the basis of a reversible interaction. So this is another thing which you need to keep in mind in terms of the principle of chromatography, is that in affinity chromatography, separation occurs on the basis of a reversible interaction between a protein and a specific ligand. What is the specific ligand? It is coupled to a chromatography matrix. So first, the chromatographic matrix is coupled with your specific ligand, and this ligand is important for your interaction with the protein. Now if it is a very tight binding, then that you cannot use such kind of a ligand, because then you can never elute your protein. If your protein has a very high affinity with such a ligand, those type of ligand cannot be said to be good ligands, because then you cannot elute your protein. But the ligand should be such that it should have a reversible relationship with your proteins as well, such that whenever it has a particular specific binding, obviously the binding has to be specific, so it should have a specific binding as well as a reversible binding. Like we should have that opportunity to throw out our protein, as well as help it to, means, capture our protein, as well as decapture our protein, or release our protein. So it should have that ability. So in what ways we can perform this elution process? So one is your pH elution, where on changing the pH, then the binding gets loosened up and you can do it. So varying the pH can actually help you. So pH elution. Then you have ionic strength elution, after which you have reduced polarity of eluent. Then you have your competitive elution, where you have two compounds and you, for your protein, has a good binding, okay, and then you use another compound which has even a stronger binding with your ligand. So what happens? It actually replaces the protein and it binds to the ligand. So this is another type of elution process. Your protein of interest just moves up, and the other compound which has a strong binding with your ligand comes and sticks with the sticks with your ligand, and then this elution process happens. And then you have chemitropic elution, so you use other chemicals for the elution process. Okay, what we have next? Okay, now we will be coming to elution. So what is the first case of elution? So the first method is the simplest case. A change of buffer composition elutes the bound substance without harming either it or the ligand. So this is the simple case where if you are using a different kind of a buffer, then it will help you in the elution process. Okay. And also another thing is that in this buffer composition also takes into consideration your pH. Now if you are changing the pH, okay, it is given in method 2 that even this buffer can also help you in elution, like imidazole. If you are increasing the imidazole concentration, you are using a nickel NT affinity chromatography, then on increasing your imidazole concentration, it will actually elute your protein. So that is a changing of buffer concentration. Now at times it might happen that only on changing the buffer composition, it will not actually elute your protein. So then what you do, you have to um, change the concentration of you say your tropic agents, or sometimes you have to reach the extremes of the pH for this elution. But also you need to keep in mind that in these extreme conditions, or at higher concentration of this cheotropic agent, it can also affect your protein. So the best thing is, and the simplest case is, your changing of buffer composition. But when you are very much interested in your protein and you need to get that protein, so some proteins behave differently. So depending on their behavior, sometimes it is necessary to change the pH and increase the concentration of these cheotropic agents. This is another important thing. And the other two methods is your, one is a specific illusion by adding of a substance that competes for binding, that is your competitive binding, which I explained you. And these methods can enhance the specificity of the media that uses group specific ligands. So if there is a competitive binding, then that compound comes and sticks to your sticks to your ligand and just throws your protein out of that, such that it can undergo elution. So that is the thing. So this is the concept of your competitive binding. And so these three are the methods of your elution which you can keep in mind. Okay. Now the purification step. Now this is your absorption versus column volume. So when you have passed 1 to 2 column volume, so this is the beginning of the sample where you undergo the equilibration of the column, then your washing steps and this and that you go. So this is the beginning of the sample. Then you start getting a curve where you are actually the absorption of the sample and the elution of the unbound material occurs. Okay, so all of the entire of the protein won't be absorbed, so there would be other proteins or other contaminants and things which would be eluted at first. So this is your first elution stage where the sample is absorbed and the other extra stuffs are actually eluted out, and then you wash away the unbound material. Then you another time you go for a 1 to 2 column volumes of your washing process, such that the entire of the contaminants or the unbound proteins are removed, and then you start your elution process where you change your buffer or you change the composition. Now you do not know how much column volume you would be requiring, so this can happen in an isocratic medium, as well as you can have to undergo a gradient where the composition would be changing in a gradient that in a gradient wise, in a percentage wise. And this would also help you. So first stage is your equilibration stage, then your adsorption of the then your adsorption of the sample and the elution of the unbound material, and then is washing of the unbound material, and then the elution of the bound proteins, and after which and then you undergo another time re-equilibration, because you cannot be leaving that column in that position. You have to re-equilibrate it, and that's all. So and then you have to dip the things in all in 20% ethanol, uh, such that there is no kind of fungus growth or your virus growth and all, and your column remains good. So this is important. So washing step is also very important, where you have to wash very properly, because you never know who has used the column before and how that person has used. So washing is very important. So sometimes you have to wash for around 30 minutes or 40 minutes, such that you are very sure that there is no contamination at all, and then you actually inject your protein. After the entire process is done, then you wash out the additional stuffs and all, then you start your elution properly, after which you have to again re-equilibrate it, such that the person who would be using the next time knows that the thing is entirely clean enough. And only so what is this equilibration process? When you are getting a straight line, it means that when you're getting a straight line, it means that now there is no other, because anything, if there is, it will be detected in the UV and you would be getting a speak. But if there is nothing, no contamination and no other unbound proteins and other proteins remaining over there, you would be getting a straight line. So that will actually tell you that now the column is ready for use. So I think I have said this. So you have to be equilibrated with your binding buffer. So maybe for 3 minutes or you use that. Then you apply the sample and wash with the binding buffer, and the entire thing is bound. You have to might be needing to collect the you say your flow through as well, because you need to also understand whether you do not know if it is a very new protein, you do not even know whether it would bind to your column or not. So you also need to collect the flow through, and after which with the elution buffer you start the elution and collect the fractions. So this is the entire thing, and these are the different graphs where you have run the binding buffer and the elution buffer. So with the binding buffer you would be seeing the peak which is of the flow through, that is your unbound material, and only when you start the elution buffer. So why there is a change in the peak or a upliftment in the peak, it is because it has a different concentration, and this is your concentration line. Okay, so with the elution buffer there is a change of concentration, and then your protein starts eluting. So if you do not change the buffer, what happens is that you sometimes get an elution, because after all it's a gradient in which you are eluting. So this is maybe you say this is the line which is from 0% to 100%. Okay, your binding buffer is running, along with it your elution buffer is running. So in the first stage it is 100% binding buffer and 0% elution buffer. And then what happens as this line starts moving, what happens is that your binding buffer starts decreasing and your elution buffer starts increasing. So in this way you can actually create a gradient. So in this manner a gradient is created where you would having a decreasing concentration of your binding buffer and an increasing concentration of your elution buffer. So this is decreasing and this elution buffer is increasing, and in this manner you can actually elute your protein. Now if you're entirely running the binding buffer, what happens, you might get a you might not get a very sharp peak. Okay, you might be getting a very faint peak or a very broad peak, which might not help you in actually eluting your target. And these are the other graphs as well, you can look into this, that sometimes what happens, so what these four graphs are, so the first one is that when you have started an elution but your protein is not showing a particular peak. So it might happen if your protein is not stable enough or is an unfolded protein, then you might not be getting a peak. Also why you not might get a peak is that, so for to get a peak what you need is tryptophan, tyrosine and phenylalanine. So it might happen that the population of these amino acids are very low, so because of this you do not get a very good peak. Okay, and sometimes it might happen that your elution starts much before your you have started your elution buffer. So there might be cases where your elution has started, the protein has started eluting even before you start your elution buffer. Also what can happen, the entire process is running very well, you get a peak, a very good peak, another peak, after some time you realize you know the peak has come to a stable point and now I can stop my elution buffer. But you never know, it can again, because it is, as I said, it is a gradient. Okay, so with the increasing gradient, at a particular gradient a protein might not elute. So that actually also comments on the different regions of your proteins, or how stable your protein is, or what are the domains associated with this thing. Okay, so this can also be an issue, that it also starts eluting but at different concentration. So you might get three peaks and you have to collect all and run it on a gel and check that which is your protein of interest or which protein you need. And these three graphs are like sometimes you cannot inject the entire of your protein at first. You have say 20 ml, but you cannot inject it totally 20 ml because it does not have the capacity. So might be you are injecting it like 7, 7 and 6. So like this you are getting 3 peaks of the unbound material, and then in the elution you get a sharp peak and you know that this is your protein. So you can undergo different ways of this. You can load the entire protein at first and it binds and the process is done in a one go. But sometimes it happens that you cannot entirely load your protein. So because of that, you have to load it 2 to 3 times or 4 times or 5 times. So you get different peaks for your unbound material, and then you get a sharp peak for your protein when you run the elution buffer. Now speaking of the matrix, so the proper selection of the matrix or the carrier of ligands is important for your stereospecific adsorption. So what should be the characteristic features of these matrix? So first of all, the thing it should be is it should be insoluble. It should be sufficiently permeable. It should have high rigidity and suitable particle form. It should have zero adsorption capacity. It should be highly rigid and suitable particle form. It should have zero adsorption capacity. It should be chemically stable under the conditions which you require for adsorption, then deabsorption and regeneration. Then the chemical reactivity which should be allowing ligands and specials should be introduced. Then this matrix should be resistant to microbial and enzymatic attack, because otherwise it would be contaminating your protein and maybe the binding would not be very proper. Okay, and then it should have a good flow properties for your rapid separation. I mean, it should allow good flow rate for your proper separation and faster separation. And an open pore structure ensures high capacity binding even for your large biomolecules. Okay, so these are the few characteristics of your matrix. So I am repeating it once more, and the important points are your insolubility, sufficient permeability, then it should be highly rigid and should be having a suitable particle form. It should have zero adsorption capacity and it should be resistant to your microbial and enzymatic attacks. It should allow a good flow rate. Okay. So as it says that no matrix support is ideal in all these respects. So porous glass, cellulose, polyacrylamide, agarose, anything can be used. So there is not a particular matrix which is uh, biasedly used or like that. So you can be using any of these, whatever suits your macromolecule or whatever suits your purification process. Now how these ligands should be selected? So the selection of the ligands, it is important because the ligand selection for your affinity chromatography is actually important for your binding of the protein. So what it should be, so the ligand must exhibit specific and reversible binding affinity. It must have chemically modifiable groups that allows it to be attached to the matrix without destroying the binding affinity. And the dissociation constant, as I was speaking, that the ligand should not have a very tight binding or a very loose binding. It should have a perfect binding of around 10 to the power 4 to 10 to the power minus 8 molar, which is perfect for your ligand, forming your ligand target complex and also for the elution process. So these are the few points which you need to keep in mind when you are selecting your ligand. First thing, it should be specific and reversible binding affinity. It should not be destroying your binding activity, and it should have groups so that you can modify the chemical groups and alter the binding thing. And the dissociation constant should be ranging between 10 to the power minus 4 to 10 to the power minus 8 molar. Okay. So let us take 2 to 3 minutes of break, after which I will be starting with ion exchange chromatography. Okay, so let us restart with ion exchange chromatography. So ion exchange chromatography, um, so your ion exchange chromatography is defined as the reversible exchange of your ions in the solution with the ions which electrostatically bind to some sort of insoluble matrix or a stationary phase. Now this particular technique is useful in the separation of charged compounds like your proteins differing by your one charged amino acid, and these technique helps you to choose whether to bind the substance of interest and allow the contamination to pass through the column or vice versa. So this technique was developed since the 19th century, which and through this technique it was used for the purification of your drinking water. And this also this type of chromatography has a distinct principle which is performed in the column. So what is the principle behind it? This type of chromatography relies on the attraction between the oppositely charged stationary phase, because as you can see or understand from the name itself, it is an ion exchange, so ions are involved. So it has to be between oppositely charged stationary phase known as an ion exchanger and analyte. Now the ion exchanger consists of an inert support medium coupled covalently to an positive or negative functional groups depending on what your protein is and what you want to separate and how you want to separate. Now to these covalently bound functional groups, the oppositely charged ions are bounded. That is, you have a mobile counter ion which will be exchanged with like charge ions in the sample having charged magnitude more than the ions bounded to the matrix. So like that competitive binding thing only. So depending on the charge, you can actually, it will actually help you to separate. Okay. Now the next thing is, now if anion exchange chromatography is to be performed, then the negatively charged sample components will interact more with the stationary phase and will be exchanged for like charged ions already bound to the matrix. So if you have to separate or you're performing an anion exchange chromatography, then what would be happening is your column would be made up of positively charged ions, and then the negatively charged ions will go and bind to this positively charged ions, and then you can separate them when using like charges, like you provide another negatively charged ion which will actually replace your negatively charged protein, and by this you can actually separate. Next, coming to the working principle. So let us consider a column having E minus and Y plus cation exchanger, in which E minus is the negatively charged exchanger and Y plus is the mobile counter ion. Okay, so X plus be the cation in the sample having charge greater than that of Y plus. So the X plus ion will exchange sites with the counter ion Y plus with satisfying the following relationship. So now first of all, your E minus is the made comprises of the column bead, and then your Y comes and binds to E minus, but X plus having higher charge and higher binding with this E minus will bind it, leaving the Y plus separate, and the Y plus will elute. So the desired bounded cation can now be eluted by either of the two ways. So what happens first is by adding a component M plus having a magnitude of charge more than that of X plus. That is, now if you want to separate this or elute this X plus, you have to provide a molecule or a component which will be having a charge greater than that of X plus. So for example, if your Y plus has plus 1, Y2 has plus 2, so your M has to be plus greater than plus 2, such that it can bind strongly with your E minus and then separate out the X plus. So this is the thing, and your X plus will be eluting out. So by changing the pH of the solvent, that is the mobile phase, so that the X plus have no charge and it's then unbounded from the matrix, can also be eluted out. So as I was saying, telling you can also change the buffer composition. Also sometimes you can change the pH. So this will also help you in elution process. So what are the factors which are affecting your ion exchange chromatography? So IEX is the short form of ion exchange chromatography. So one is the ion exchange resin, that is the swelling factor, and the cross-linking is important for the effective separation. The cross-linking should be controlled as it affects the exchange's capacity, and swelling helps in proper exposure of the charged functional groups for the exchange of ions. If it swells less, then the separation of the ions of different sizes becomes difficult. Now the nature of the exchanging ions depends on your valency of the ions, then your size of the ions, then comes your polarizability, after which we have the concentration of the solution and the concentration and charge of the ions. After which the factor which is also affecting is your pH. So the pH of the mobile phase also affects the ion exchange chromatography. You can tell the ionic strength also affects your ion exchange chromatography. Definitely temperature plays an important factor over there. Also you have other modifiers, namely your mobile phase modifiers. Then ultimately it comes to your buffer. That is very important, and this is a very important factor for any kind of chromatography, not only ion exchange chromatography, but if you speak of any kind of chromatography, these buffers are very important. So you need to keep in mind these factors which are actually important for your ion exchange chromatography. Out of this, mainly which you have is the comment which is made on the resin, then the nature of the exchanging ions which you would be using, definitely the pH, the ionic strength, temperature plays a role over there also, and you know about buffers, because the pH of the buffer should impart the same charge to the sample ions as present in the column. Then anion exchange chromatography should be carried out with the cationic buffers, and vice versa, because the buffer ion will indulge in the ion exchange, which will be of no use. So that is why you need the buffer also is an important factor in this kind of chromatography. Now, if we classify the ion exchange resins, so according to the chemical nature, they can be classified as your strongly acidic cation exchanger, which in which you have the sulfonic acid groups attached to your styrene and the divinyl benzene copolymer. After which you have the weakly acidic cation exchanger, which includes your carboxylic acidic groups, which is attached to your acrylic and the divinyl benzene copolymer. Then you have strongly basic anionic exchanger, which is the quaternary ammonium groups attached to your styrene and the divinyl benzene copolymer. And the weakly basic anion exchanger, which has the polyalkyl amine groups attached to your styrene and the divinyl benzene copolymer. Okay, so basically it can be either styrene or acrylic and the divinyl benzene copolymer, or the styrene and the divinyl benzene copolymer. So this can be the two, and then you vary these different groups to make it a strongly acidic anionic exchanger, or a weakly acidic cation exchanger, or a strongly basic or a weakly basic anion exchanger. Okay. So the different applications of this ion exchange chromatography includes the softening of hard water, then you have the demineralization of water, then you have, if you want to analyze the base composition of nucleic acids, it is important. Then if you have to measure the additives in the foods and the drug sample, this plays a very important role. If you need to concentrate metal ions in the sample, it is important. Then when you are separating protein mixtures, then extraction of the enzymes from the tissues, then it also helps in the separation of inorganic ions, then your separation of sugars, amino acids and proteins. Also, it helps in the purification of your solutions, which are free from ionic impurities. And this ion exchange column is also used in your high pressure liquid chromatography. Okay, so these are the different applications in which you can observe this type of chromatography being used. Okay, So with this, we come to the end of the discussion part. Now I would be discussing a few practice problems with you. So as I do in my every lecture, so you would be the people who would be giving the answers first, after which I would be telling you and discussing with you the answers. Okay, so let us start and see. I think we have only one candidate. Okay, you can only try. Let's see what is the answer of the first one. So what does the first question say? It says a particular protein can be separated from other contaminating proteins by mass spectrometry, fractional distillation, chromatographic techniques, D, all of these. C. Okay. So yes, that is the correct option. So chromatographic techniques is the correct option. Okay, coming to number 2, during gel filtration chromatography, separation occurs on the basis of charge of the protein, pi of the protein, shape and charge of the protein, shape and molecular weight of the protein. Okay, I think I've got an answer. Did I? Yes, so you have said D, that is right. So we separate during when we perform gel filtration chromatography or the size exclusion chromatography, we separate it based on the shape and the molecular weight of the protein. Now the next question. So these are very easy questions. The matrix used for gel filtration chromatography varies according to their pore size, molecular weight, charge, functional groups attached to the matrix for a size exclusion chromatography or a gel filtration chromatography. According to the molecular weight. So the question says the matrix used for gel filtration chromatography. In gel filtration chromatography, we separate it based on shape and the molecular weight of the protein. But what is the thing for about the matrix? Okay, so if you look back to my slides, I was speaking about the beads, the pores. Yes. So the pore size is important. So the matrix which we use in the size exclusion chromatography should actually be varying according to its pore size. We separate different molecular weight proteins. It is not the molecular weight of the pores that is actually important. It is the pore size to which our different molecular weights of the proteins would be binding, or the different proteins that would be binding. So that is not the thing. The pore size is important. Yes, so A is the correct option. Coming to the next question. It says number 4, in case of thin layer chromatography TLC, the stationary phase is usually, I haven't spoken of thin layer chromatography, but what can be used in a thin layer chromatography? I was saying in one of my slides about one of these. No, actually not all of these you can use in thin layer chromatography. So thin layer chromatography is what? It is actually it's actually made on a slide. Okay. Where you have to actually make the stationary phase. So on a slide you are actually making the stationary phase. So this stationary phase is actually made up of your silica. So this silica will actually be the stationary phase for the case of your thin layer chromatography. So D is not the right option, B is the right option. Silica would be the right option. Okay, no problem. Void volume in a gel filtration chromatography column refers to the. So what is a void volume? You've given an answer of B, volume of the column. Is it so? No, B is not the right option. So void volume is the space outside the matrix granules. Okay, so that is why it is not the right option. So as I was speaking, so void volume is the one when you have very higher molecular weight proteins, then if the entire thing passes out without being without having any affinity for the pores, or if they do not enter the pores at all, then that is termed as the void volume. Okay, so the right option, now can you tell me which is the right option? Yes, so C is the right option, that is the volume of the column which is unoccupied by the matrix granules. Okay, the next question is a longer question, it's a bigger question. Okay, so it says three different proteins are to be separated for analysis. The characteristics of the proteins are given below. Which of the following would result in the best separation of these proteins in order to get them in the pure form? So protein A has a molecular weight 13.3, PI 9. Another one has a molecular weight 27.5, PI 8.7, and the other one has a molecular weight of 63.4 and PI of 9.5. So which of these chromatography techniques you would be using and why? Okay, you say B. Okay, tell me why. What could be? You can tell me in short as to why and why we cannot use other chromatographic techniques. That is one point is correct. We have molecular weight. That is very correct. They have varying molecular weight. Separation would be based on size. That is also very correct. Right answer. And another thing you need to keep in mind is that the PIs are very close to one another. Okay, so they cannot be separated based on ion exchange chromatography. And SD, when you are running an SDS page, you are giving them an means entirely a chart. You can see them. Okay, you can observe this protein, but if you tell me whether we can separate this, no, because this is when you're running an SGSP, you're giving a uniform negative charge to all these proteins and they would be running based on their size. That is absolutely correct, but you never know whether these proteins are either monomers or dimers. Also there can be a question like, can you comment on their whether they're monomers or dimers? So if these are, so it's 13.3 and 27.5. So it is possible that B is a dimer of your A, and also it might be possible that C is a tetramer of your A. Possibility is there, or a dimer of your B. So that's why when you're running it on a SGS page, if it is a dimer or a trimer, you will see all of them running together. That's why you cannot separate them. So therefore you do not know whether it's a dimer or a trimer or any other polymer. So that's why gel filtration chromatography is best. So where you can also separate if even if the proteins are not monomers, and it will also help you in commenting these gel filtration chromatography about the property of the proteins, like if these proteins are in dimer or tetramers, right? Okay, yes, molecular weight and based on size is correct answer. Okay, let me see what comes next. So affinity chromatography deals with the specific binding of a protein with another molecule, protein DNA interaction, protein carbohydrate interaction, charge of the protein. It's a very easy answer, affinity chromatography. So A is the right option. A is the right option, that is specific binding of the protein with another molecule. Question number 8 says, once a protein comes out of the gel filtration column, it is usually monitored using. So which of these we can use for the monitoring process? So you say C, that is UV spectrometer for studying the absorbance. Yes, the event is analyzed using the UV spectrophotometer, and then you detect the protein by studying the absorbance at 280 nanometers. Okay, so question number 9 says carboxymethyl, sorry, carbox carboxymethyl matrix and diethyl aminoethyl matrix are generally considered as cation exchange matrix, cation and anion exchange matrix, respectively, anion exchange matrix and anion and cation exchange matrix. You say both are cation exchange matrix. Okay. So carboxymethyl means it has a carboxylic group. That means this matrix is itself negatively charged. So you tell this is a cation exchange matrix. That is correct. But the next one is diethyl aminoethyl matrix. So it has an amino group. So it will be positively charged matrix. So what the answer should be? So the first one is a negative one. So it can be used as a cation exchange matrix. But your diethyl aminoethyl matrix is a positively charged matrix, so it should be used for the separation of the negative ones. So it will act as an exchange matrix. So option B is the right answer, that your carboxymethyl matrix will be a cation exchange matrix and your diethyl amino ethyl matrix will be an anion exchange matrix. You got it? Yeah, good. What is the next question? Before loading the protein onto a chromatographic column, the following treatment is made to the column. It is equilibrated with the protein which is to be isolated. It is washed with ethanol to remove the impurities. It is equilibrated with buffer which will be used as the mobile phase, or it is washed with the matrix solvent. Which of these is correct? It is washed with ethanol to remove impurities. It is okay, but see what the question states: before loading the protein onto the chromatography column. Just before loading the protein, you do not wash it. You wash it in the beginning and you wash it in the end. But before loading the column, yes, it should be equilibrated with the buffer which would be using as the mobile phase. Then it is okay. Okay, the next question is, a sample contains a protein, mixture of proteins, which the protein X is to be isolated. Which method of we will be using for accurate isolation? So different PIs are given, different molecular weights are given. Tell me. And why, definitely. Ion exchange chromatography only, or ion exchange followed by gel filtration, then affinity followed by ion exchange, or the gel filtration chromatography. Hence the question says X has to be isolated. How would we be isolating X? You say A. Only ion exchange chromatography would be sufficient to isolate X. Okay, I understand your logic because you have already stated before. I understand that because the PIs are not very close to each other. But if you see that the PIs are actually close to each other, like 3 and 4.3 are close to each other, and your 8.7 and 7.4 are close to each other, right? So yes, you can separate them using ion exchange chromatography. That is true. But here you would be requiring two types of chromatography. What? Only now if you perform only gel filtration, it would give you a mixture of B, C and X. You know why? Because they have similar molecular weights. So only doing gel filtration chromatography won't work over here, and only ionic chromatography would give you a mixture of A and X. So that is also not possible. So how you do that? Now for B, C, X you got, and then you get A and X. So first you do is separate this A and X. Okay, so first you perform ion exchange chromatography and you separate A and X. So the A is gone, and you separate this A and X thing. After which what you do is you go for your gel filtration chromatography. In this way you can actually separate your X from B and C. So in this manner, so the correct answer is B, where you perform your ion exchange followed by your gel filtration chromatography. Because in the if you perform only ion exchange chromatography, you would be getting A and X together and B and C. If you do only gel filtration, you would be getting B, C and X. So perform ion exchange first and then gel filtration. Then you would be actually separating. Firstly, A would be separated from X and then you would be separating B and C from X. Coming to the next question, your protein of interest contains a 6x histidine tag and is overexpressed in bacteria culture. After purifying by nickel NTA, you run the eluted fractions through an SDS page to confirm its presence and purity. However, you observed in addition to your protein of interest an additional band, which is what of this possible explanation is for this? The his tag got cleaved, the protein does not contain a tag. In addition to your protein, some bacterial protein also contains tandem repeats of histidine residues. The protein is multimeric. So his tag actually binds to a nickel NTA column. Okay, so his tag actually binds to nickel. So what could be the reason that you're getting another band? Means you're also getting that protein as well. So what could be the reason that it is that protein is also binding to your nickel NTA affinity chromatography, or sorry, the nickel NTA column? What could be the reason? See, yes, there might be some bacterial proteins which has repeats of these histags, because of which that histag is also binding to that column. Okay, so if some bacterial proteins has those kind of repeats, then actually you would be this would also come out with your protein of interest. Okay, so yes, C is the right answer. Number 13 says, why is it advisable to degas the mobile phase in case of gel filtration? Under high pressure, air is trapped in mobile phase are removed, which would otherwise hinder the flow of the mobile phase to the matrix. Degassing makes the sample stable in the mobile phase. Degassing removes contaminant from the buffer. Which is the right answer? Oh, D says all of the above. Why do we need to degas the mobile phase? I haven't spoken anything of degassing, but actually it releases the pressure or the air which is trapped in the mobile phase, and which would be affecting the flow of the matrix, because this gas would be acting as a barrier and this would be affecting the flow of the matrix. Therefore, it is very important to degas the mobile phase before you are actually loading your sample or actually letting the mobile phase flow through. So number 14 says, in FPLC system, usually the flow rate is maintained at 2 to 5 ml per minute. Increasing the flow rate beyond the limit can cause column breakage, heat up the column, damage the proteins, all of the above. Column breakage. Very right and very correct. So the FPLC columns can withstand a certain pressure generated by the flow rate of the buffer, that is your mobile phase. Now if you increase the flow rate beyond the limit which is given, now due to high back pressure, so there would be a certain back pressure as well. Due to the increased back pressure to the column will also get damaged, and ultimately it will lead to column breakage and will hamper your entire process. That's why the flow rate has to be maintained within this limit. And the last one says, when not in use, the gel filtration column as well as all the tubes in the FPLC system should be stored in 70% ethanol, 20% ethanol, deionized water, 0.02 molar HCl. I think this is the easiest question of all. You can answer it. He was speaking of one thing, that it should be to avoid fungal bacterial growth, the tube should be dipped in. The tube should not be dipped in HCl. No. D is not right thing. Now you basically have three options left, because I've already said D is not right. So the tubes have to be dipped in ethanol. Okay, so what is the percentage of the ethanol you should be dipping your tips in? That is important. Yes, they asked not in use. So when not in use also the tube should be dipped in such that even if you do not dip the tubes in something, then what would happen? These tubes are outside. Okay, and there are chances that first of all, forget about the bacterial and the fungal growth. There is dust all around. So first, there would be a dust layer coat. I mean, there would be a dust coating on these tubes, and this would actually go inside when you are injecting your protein and running your buffer. So when not in use, it should always be dipped in some solution, and this cannot be a solution like your buffers as well, because your buffers have salts. It would be salt decomposition, and this would block the columns and block the tubes. So it has to be dipped in something. So it has to be dipped in ethanol. It has to be also cleaned with water, buffer, ethanol. It is also important. But when not in use also, there has to be dipped in something. So we dip it in usually 20% ethanol. We also do not give very high percentage of your ethanol or very 100% ethanol. It has to be dipped in 20% ethanol such that it is present in a solution, and this ethanol environment does not allow the growth of any other fungal microbial organisms. Okay, so okay, that's all. Then thank you from my part. If you people do not have questions, okay, that's all. Then we end our session over here. We will be meeting you in the next week with another live session. Actually, means for this lecture you're saying, or for any lecture? So I have a YouTube channel with my name, and so yeah, I have a YouTube channel, and then I'm uploading the lectures over there only. So it actually, so the title of my lecture starts with experimental chemistry, then your week, and a particular week, and then live session. So if you go into this, so I have given it in like this pattern only. So week 1, 2, 3, 4, 5, and I will be uploading in this manner only. So actually you are supposed to get these lectures from the NPTEL team. Okay, I cannot share you, means if you are if you mail me, I can actually send you the link, but actually this is supposed to be shared by the NPTEL team. You can contact the NPTEL team if these slides and these lectures are not being shared, or the YouTube link is not being shared with you people. Okay. Okay, okay, thank you.